comfortable in your chair because today we're going to use war tactics to make an unbearable object. I'm going to reverse engineer an industrial siren. Just for the record, there are people here at Manual du Mundo who don't believe in this, who are saying this thing is going to go wrong, you know.
One of the people who think it's not going to work is me, because I've already seen the team testing. I'm already hearing it scraping, 3D printing, taking it apart. It's not going to work.
This beautiful thing. Here in my hand is an electromechanical siren. It looks really old, maybe 60 or 70 years, and was probably used in a factory. I bought it at an auction for about 200 reais. Used, of course, but a new similar siren would cost about 1,000 reais. When I bought it, I wasn't sure what to do with it, but then we went to make that video showing why. The ambulance siren gets higher pitched when the ambulance is getting closer to us. So we put this on top of a car, tied it up, went to a test track, and this siren stayed on for about 40 minutes. That's when, unfortunately, it couldn't take it and died. If you think I'm taking this siren apart to check inside and repair the motor, no. We're going to do something better. What I'm going to do today is called reverse engineering. What does that mean? It means someone takes a piece of equipment that they didn't build themselves, then they observe it, actually take it apart to find out how it was made, to build another one, or maybe to pick up on some technology that's in there that you don't know yet, or to build a machine that makes that equipment. As you might guess, this is widely used in war. So the enemy captures equipment with technology they don't yet know. They disassemble it and build their own equipment from it. Classic example of wartime reverse engineering. The B-29 was the plane that dropped atomic bombs on Hiroshima and Nagasaki. The Soviet Union accessed a United States plane and created the Tupolev Tu-4. Look at how it's such a coincidence that the two are so similar. But there's a case that really highlights the danger of reverse engineering. In 2011, the United States was after Osama bin Laden, who was the head of Al-Qaeda, the terrorist organization that carried out the September 11 attack in New York. They knew that Osama bin Laden was living in Pakistan, and they set up a secret operation, secretly, to Osama bin Laden's house and kill him. So what did they do? They took 2 of those Black Hawk helicopters, which are really famous in war. But these were helicopters prepared to make no noise. They were stealth helicopters, a technology no one truly understands. They sent 2 helicopters with Navy SEALs, these highly specialized guys, maybe not even soldiers, but extremely skilled at their jobs. And these guys were going to rappel down on Osama bin Laden's house. But when they got there, one of the helicopters lost lift and made a forced landing, crashing to the ground. The helicopter broke. They continued the mission by entering the house and killing Osama bin Laden. Several people took his body. Other helicopters provided cover. So when it was time to leave, they used another one. Now just imagine leaving behind a super high-tech helicopter with a bunch of features that make the helicopter silent. Then all Pakistanis could access it. You know what they did? They used explosives to blow up doors and other things. They placed some under the helicopter, destroyed it, set it on fire, and left. Because just imagine if someone got their hands on that valuable thing. But luckily, we're not dealing with military equipment. So the Siren seems a bit easier to take apart than the Black Hawk was. I've already removed the front cover. However, the back part isn't that easy. I'm not interested in the motor since I won't use it from this model. I'll just use this front part here. What I've done so far might already be enough. Look how nice. It has a wheel here. This wheel directs the air out, right? When it's spinning, the air tends to escape through these holes. But there's a cover here. Look, that makes it so sometimes the hole lines up with the outside one. Sometimes it doesn't. Sometimes the air escapes, sometimes it doesn't. It's like a compressor that keeps releasing and stopping air. Crazy, right? What's the logic behind this? The logic is very similar to a speaker. Sound is air vibration. So the speaker keeps vibrating the air. So this shaking of the air reaches our ears. For that, the speaker's diaphragm keeps pushing the air. In this case, we have a machine that kind of spits out the air in little bursts like a speaker pushing. And of course, I'm not doing this here without having studied it a bit first. So we built this thing to show you this principle. This is basically a musical siren. Each musical note has a number of vibrations per second, right? It has specific hertz. If it were a speaker, for example, it's how many times the speaker pushes out the most common note, the one we hear the most. It has 440 hertz, meaning the speaker moves back and forth 440 times. I've already programmed this with the notes B, A, G, F, E, C, like a musical instrument. I thought putting a drill here would make some noise. I didn't want the sound of a drill getting in the way. So what did I do? I put a pulley with a belt back here. Look, when I turn the crank, the disc spins almost silently. There's a little bit of noise, but it's much less than if it were a drill. And the idea now is to blow into these little holes. And the same thing as the siren will happen, right? The air will be able to pass through at one moment and then not at another. It passes, it doesn't, it passes, it doesn't, it passes, it doesn't. This causes a vibration, and we'll get musical notes. I mean, that was the plan, right? Whether it's going to work or not, we're about to find out. Let's hold the little guy here to see if it works. We need to give it a push because the reduction here is pretty big, right? I'll turn it a few times on this side, and it spins a lot on the other. I know I need another bearing, but this aluminum isn't very centered. Let's go. It made me dizzy. There wasn't any noise at all. I think my blowing is too weak to make any sound here. Let's get something stronger to blow into the little holes. I forgot about the shoulder surgery, but the doctor isn't watching this video. Here we go now. Let's see. Look. What's happening? Wow. The compressor's out, so I'll need to refill the tank. Here we go. Look, just listen. Just listen. It's tough to turn. Come on, let's force it. Whoa. The battery's dead. Whoa, but today is the day. Look. I swear to you guys, this morning I went to buy the belt by the meter, glued the belt, made all the pulleys here. We worked to design this thing with the laser, but anyway, we're gonna have to use the drill after all. Here we go for the 15th time. Start slowly. Is my theory approved? Doesn't it sound like a siren? I'm going to put on some ear protection because the people here at Manual complained that the volume is absurd, that it's loud outside, and I didn't notice. So I'm also going to measure it with the decibel meter here so we can compare and see what the volume is, if it would be comparable here. Let's do it now, all right? If this isn't worth a thumbs up, I don't know what is. Can you say you've ever seen a musical instrument like this in your life? If you haven't, please like and subscribe to this channel. This is wild. It even slipped out of the bearing. Let's check the decibels. 120.6. According to this chart, this sound volume is equivalent to a jet plane taking off if you're 7 meters from the turbine. Eld. At the airport, people near planes should definitely wear ear protection. The question now is, will the siren, we're going to make imitating this one, be as loud as this? Let's get to work. The first step here will be to measure everything very precisely. I want to make it exactly the same way, as similar as possible. And then I sit at the computer and start drawing in 3D here, these parts. I'll spare you all the details because it takes several hours of modeling. Here, I started with this part, which I'll call the rotor, okay? The part that spins, maybe the most important of all. I modeled it almost the same. If you look here, these inner blades on this part are pretty straight. I made a slightly more organic design. I'm not sure if I got it right. My idea is that the air flows a little better. Maybe I made a mistake here, but let's see. You can see that there are the same number of outlets here. There are 6 outlets on this part. I made 6 outlets here as well, and there's a hole in the middle, which is for placing this aluminum shaft. It fits exactly on the aluminum shaft. Extended this neck of the hole a bit, so we can secure it well to the aluminum. Besides that, what else will we have? This piece with these openings is where the sound comes out. Let's check it out. It's this right here. You can notice that at the air outlet here, there's a kind of cut. It looks like a blade. Is it sharp? Just like it is here. I just didn't make this central separation because I imagine it's more to protect people's fingers than to help with the sound. But anyway, this needs a front, right? I also made a front cover, which is right here. Look, it's full of small holes. And it has a support in the center, which is for me to put a bearing. This little piece, okay? This bearing will fit here, and it's to keep the shaft nice and straight. My shaft isn't as strong as the steel one. It's more flexible, so I need a bearing here in front. Mom, yell at me. That should be a single piece. Why are you making 2 different pieces? Because I need to optimize it for 3D printing. So, look with a different piece. I can have a flat part, flattened, that fits on the print bed, so it sits perfectly on the print bed. All right, let's go. On the other side, we'll have a closed cap. Okay, I also made a support here for the bearing. It corresponds to the base of the motor. We're not going to make the motor, because I'm just going to put a drill here. That's basically it. One extra thing I did are these 3 little points. They're for putting screws in to align everything and secure it at the end. Besides that, I also made a little spacer. It's a really small piece. Here it is. Look, it wraps around the shaft to adjust the rotor inside so it doesn't move and hit the edges. Okay, and there's one more thing I made, which are 2 pulleys that we might need to use. These are the pieces here. Because I suspect that the drill's rotation is too low, it spins much slower compared to this motor. So, we're going to have to speed up the drill, and I'm going to have to do it like a bicycle gear here. Let's print this thing. This turned out to be the most beautiful thing in the world. There are 9 pieces. I tried to avoid making this kind of support here on the 3D printer, right? It's like scaffolding for the 3D print. There was no other way, since some parts like these pulleys need support. I have to tell you, it's really cool to draw something on paper, then move it to the computer, model it in 3D, and in the end, have a real-life object come out, solid and sturdy with a nice look. Let's start assembly by fitting the bearings into the slots. They fit tightly. One thing I learned while making this video is that Siren means mermaid. Yes, that's exactly what you heard. In fact, if you look up mermaid on Wikipedia, you'll see that one of the names is Siren. Even in Spanish, it's Sirena. That's because, in mythology, mermaids were beautiful women who stayed by the sea singing. And their singing would enchant sailors. They would get kind of dazed by the mermaid's song, drawn in by it, and would end up crashing their ships into the rocks and sinking. So, when someone says they heard the mermaid's song, or calls a story a mermaid's song, it means they're being lured into danger. Like, I don't know, someone trying to convince you to get rich using a betting site. Okay? But what do these women who sang have to do with an instrument that makes a really loud sound? The siren was invented around the early 1800s. So, in 1819, a Frenchman named Charles Cagnat de Latour managed to build an archaic siren back then, which he called
Siren?
Which is mermaid in French. It was a machine so loud you couldn't ignore it, like a siren song. Do you think perfect alignment eliminates all noise and friction? Of course, when I was drawing it, I measured the screw and made it exactly the size of the screw. I even left a little bit of clearance, about 1/10 of a millimeter. The problem is that with 3D printing, when the machine releases the plastic, it ends up spreading a bit to the edges. So when you make any hole in 3D printing, it always ends up tighter than you designed. And the edges of the material always end up a bit bigger than you designed as well. I have a small issue. I need to open the thread here with the drill 1, 2, 3. Fernando, you said this wouldn't work. But it's working. It's making noise when I turn it by hand. Theoretically, if I put the drill here, this thing should already be singing like a siren, but I'm making a backup, like I showed you in the drawing over there, which is to put a pulley to speed up the thing. So let's fit this pulley here, which, as usual, doesn't want to go in either, right? And I forgot to put a part in here. Look, it's loose because I didn't put one of the spacers in. Look, this little piece here was supposed to go inside. It won't let that happen. The project was done well, right? Let's get it right this time. This will fit perfectly. No more looseness, just nice and tight. Let's sharpen the shaft tip and see what happens. It's easier this way. See, it goes in, but I think I need to make the shaft smaller. Hey, Mr. Osvaldo, you're always in my way, aren't you? Hey! Look how beautiful this is. Let's secure everything to the table now and keep a belt nearby just in case. The little machine is ready. Let's test it. This is the original project, and this is the reverse engineering. I'm going to start with this little screwdriver here since it's pretty weak. In fact, its chuck doesn't even fit on the shaft here. This is a much bigger drill. I bet it'll work. It started making some noise. Actually, with the ear protector, I can't hear it. I don't think it's that loud. Let's test it again here without the protector. I'll tell you guys, this drill is already all dusty. We hardly ever use it. Look, it's already messing up because it's a much heavier drill. It needs to be plugged in, but it's faster than the others. Look, we already have. Let me unplug this. We already have half a Siren here. It's already making noise. But exactly what I was expecting happened. The drill's rotation doesn't make much noise. It just goes vroom and can't get any louder. What I'm going to do now is use the last piece that's left. This works like the chain ring on a bicycle, and this one is like the sprocket. You put the big chain ring with a small sprocket. We multiply the speed. So here I'm going to multiply the drill's speed by about 3 times, which will give a much higher pitch. I didn't make a support, so I'll have to hold it by hand and attach it to the drill. I think this will give a different result. I think it's best to wear ear protection. We have a Siren made with reverse engineering. And it sounds nice, doesn't it? The drill spins at 2,500 revolutions per minute. I multiplied that by 3, so it's about 7,000. But the Dremel is this little thing here. It reaches 33,000 revolutions per minute. Not sure if we can attach them, but I think the noise will be higher pitched. Will it? Look, it's spinning well and keeps going for a while. "128 decibels. Take a look at what that means in the real world. Right, because just that number doesn't mean much. But it's louder than a plane taking off. It's equivalent to a thunderclap. After all that, I decided to do something else here, which is this: instead of attaching the belt to this pulley, I'm going to attach it directly to the shaft. The shaft is smaller, so I'll get a much higher speed. It'll accelerate, right? It will boost the speed by about 20 times, matching the ratio between this wheel and the shaft. Let's see.
This noise here means it worked right.
It worked really well. Okay, here, Lindy. We proved that we are capable of doing decent reverse engineering with everything aligned, neat, working perfectly on the first try. And you also learned what reverse engineering is. And that Siren is called that because of the mermaid. You don't learn that just anywhere, right? That was worth signing up for Manual do Mundo, wasn't it? If you like loud noises, once we decided to measure the speed of sound. For real. We used a recorder and a firecracker for that. This experiment is cool. Check it out.